Is on 555 timers for hobby electronics. It is a little bit different than our previous deep dives because this is an integrated circuit. The way that Electronics Club worked last year before COVID was all workshops centered around a integrated circuit. And we'd spend the entire time learning about how the integrated circuit works and then trying to build a circuit around that integrated circuit. That's how a lot of hobby electronics works in general. We don't really want to work with inductors and capacitors and transistors at the base level, especially if there's already something that does that. It is similar to programming in the sense that if there's a package that already does that, just use the package, don't reinvent the wheel. So what this does is that instead of reinventing the wheel, or in this case, an oscillator, we use this IC. So here we go. Starting off, some contact info. Same stuff it's been all year. I still am doing office hours, 7 to 9 p.m. Thursdays. This Thursday will be our last office hour, and then this is our last meeting of the semester. There are still open officer positions, social media webmaster, funding coordinator, and e-council rep. Send us an email at that email if you are interested. All right, so content overview. Similar to our previous deep dives, because I like to stick to a format. We're going to go over some overhead theory and then get into more practical stuff, starting with what a 555 timer is. What does it do? How does it work? And then we're going into more practical stuff. How do I work with it? And what can I do with it? So if you'd like to keep up with the slides, there are some slides that you might want to kind of keep in a different tab that we'll get to later. So I recommend opening this up. I will post the link in chat as well, as Edward already did. So what is a 555 timer? Well, it is an extremely common precision timer IC. Can act as either a timer or an oscillator, or as we'll see later, a flip-flop. It is very, very common because it's easy to use and it's really inexpensive. I think I have a little picture there. It's $50, 2 quarters. There's a quote that was here from the workshop. I don't know who it's by. We'll say Albert Einstein. It is the most popular integrated circuit ever manufactured. It is used in a whole lot of applications. So learning this is a very good thing. How does it work? We have some innards here. So you'll see 2 comparators, an NPN transistor, a flip-flop, and where it gets its name from is from 3 5 kilo ohm resistors, all in a row. So there's 2 comparators. They go into something called a flip-flop, which if you take digital electronics, essentially just stores values. You'll see in the kind of challenge example how we'll try and use it as a flip-flop. But the cool thing about integrated circuits is that we can look at this and we can figure out how it works and why it works. Or we can pretend it's a big black box and not think about it. So we have a lot of our kind of tools that we need. We did previous meetings on NPN transistors. You can look up how flip-flops work. It's essentially a like a logic gate. You can kind of think of it like that. Comparators are not terrible. If one side is larger than another side, then you have an output. If it is not, then you do not. So if you really want to sit down and learn how this works, you can, but we don't need to. So there's 2 operation modes, monostable and astable. The first one, monostable, is what we were referring to as the timer mode. It waits a certain amount of time, and then it sends out a pulse for a certain amount of time. And then it waits for a certain amount of time and sends out a pulse for a certain amount of time. And this time is determined by an external capacitor and an external resistor. So having these two kind of control points is how we control when the timer kind of sends out a signal. So that's a design choice where we get to choose how long that is. And we can actually make that variable if we have a potentiometer. We can hook this up to our kind of resistor value and switch it back and forth, and that'll change kind of the delay period. I think in the workshop last year, that's actually what we did. So if you switch it all the way to the left, the delay period gets shorter, so it happens doop, doop, doop. Switch to the right with a higher resistance, delay time is longer, so boom, boom, etc. You'll see the kind of diagrams on the right just showing exactly what I'm talking about. The formula for how long the dupe is the resistance value times the capacitor value times this random constant 1.1. I will post the PDF later if you would like more context. I put an extra question mark here for extra emphasis. That was an accident. But what does it do? In astable formation, this is the second kind of common mode of usage. It is called oscillator mode, and it acts as a kind of rectangular waveform generator. The output is adjusted by two external RC charge/discharge circuits. On the diagram, it is essentially just some resistors and a capacitor. So the kind of variables that you're worried about in a square wave, two of them are duty cycle and frequency. And the way that these are determined are kind of written here in some formulae. So you see that on the graph, the voltage goes up to a higher value around 2/3 of the VCC as a cap, and it'll go down to 1/3, and then it'll go back up. So when it goes to 2/3, the flip flops and it goes back down. When it goes to 1/3, the flop flips and it goes back up. So the reason this is called astable is because the voltage goes above zero at a minimum and goes back down. While monostable, you'll see in the input, it goes all the way down to zero and all the way up. Hello, we have a new joiner. We were talking about the two forms or the kind of two uses of a 555 timer. One of them being monostable, where we have a kind of timer where we have a doot, 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 and we can use resistor, capacitor to control how long between those doots. And then astable, where we're essentially creating a wave, a square wave. The thing about this particular configuration is that the duty cycle can only equal T high over T high plus T low, where T high in the diagram you see is how long the doot is, and T low is how long you're waiting for the doot. The problem in this configuration is that when you have that as the duty cycle formula, you can't get below 50% duty cycles. And if that is a problem for your application, there is a slight variant where you can add a diode. Getting back to the usefulness of diodes, with this, you can get below a 50% duty cycle. So what can we do with it? This is the more kind of interesting part. One of them is an LED flasher. This was a full workshop last semester, or not last semester, but last year. And we can actually recreate this in Tinkercad. Tinkercad has a whole bunch of ICs, and one of them is the 555 timer. As a matter of fact, I did. And you can too. This is our circuit diagram on the right. I highly recommend looking at the circuit diagram and not looking at the Tinkercad example here. I think I talked about this in a previous meeting. This is one of the reasons why looking at a circuit diagram is much more useful than looking at Tinkercad. Because the Tinkercad is very messy, circuit diagram is very not messy. Important things when you're looking at ICs. There's like a little circle that like orients where the first pin is, and that's how you figure out what the other pins are called. The thing I Google all the time is something like 555 timer pinout. I think I mentioned that before as well. It is always good to look up your component space pinout so you know what the pinouts are. So yeah, we can spend a good like 10 to 15, maybe more minutes if you guys want to actually do this in Tinkercad. I think I might be able to share what it should look like. If I, here we go. So I'm going to stop screen sharing on my iPad real quick. I highly recommend getting your own slides out, going to electronicsclub.com real quick. So let me put that link in chat. Edward, stop messaging. There we go. So if you go to that link, go to the slides, you'll be able to watch this as I turn off my screen share. Oops. And then turn on my screen share here. Let's see. So I actually ended up doing this in Tinkercad about 20 minutes before this meeting started. It was more of a scramble, but once you get everything functioning correctly, you'll see a oscillating LED. And I think if we change this resistor value, we can change how frequently that pulses. So now it's pulsing more frequently. Now it's very bright too. So this is what it should look like, and I will go back to the diagram. All right. So 10 to 15 minutes. So we'll call it at 6:37. Yeah. So 6:37. Let me know if you have any questions or if you want me to look at your circuit. And I will see you then. I actually do have some 555 timers on me. It is not terribly interesting to look at, but important note: the transistor, some BJT notation, right? Reminders. The input. This might be better to kind of draw a diagram. So a quick reminder, this is a NPN transistor. So you'll see it on Tinkercad something labeled C, B, and E. And this picture will show the pinouts for that. So, yeah. even more notes. The capacitor will have the anode, the side you want to be negative, has that gray line on it. How is it coming along?
Got Tinkercad working. I'm gonna see if I can whip up a breadboard circuit real quick.
Cool. I am doing the same thing. It should be noted, you can do this in with an Arduino. It's actually really easy with an Arduino. Something like right pin high delay for a certain period of time, right pin low delay for a certain period of time, and you'll get essentially the same kind of waveform. The reason we don't use a microcontroller all the time is because that'd be very expensive for a very simple function. And sometimes the microcontroller is less stable because it is very kind of cumbersome. It'd be kind of like using a whole personal computer just as a calculator. Specifically as a calculator that needs to do a whole bunch of operations very quickly. All right. I think I might call it there at 6:36. But feel free to try this in Tinkercad, or we have plenty of 555 timers in the workshop. I'm not entirely sure what the workshop hours are going to be going in here. Probably not great since we're leaving Thanksgiving. So the workshop will probably be open if we have an in-person semester next semester, which I am hoping we do. Otherwise, order some on Nouser Electronics or Jayco. Make it a winter break project. They are very cheap. So going into other applications for what can I do with it? You can drive relays. They're any one-shot timer circuits. So like a metronome. If you need the doop doop, just hook it up to a speaker. Bounce-free switches to make sure that when you press a button, you get only one press and you don't get a whole bunch of oscillations in there, which is a problem with analog circuits. You make a triangular waveform generator, so just a square waveform, and then you do something to it to get a triangle wave. And then on the data sheet, they had some interesting use cases for fingerprint biometrics, iris biometrics, and RFID readers. Which kind of speaks to me as a company trying to like sell their super IC that can do these really interesting stuff. So I'm not entirely sure how 555 timers are used in these things, but it is a good example of the fact that 555 timers are used everywhere. I think in like Make Ohio, RFID readers are actually pretty popular. That's a pretty popular project. So if you ever do that, you might use a 555 timer. So some important kind of design notes. Oof, for the 1K resistors. So some important design considerations are listed here. Depending on what your supply voltage is, what the supply current is, what you want the trigger current to be, and what you know your frequencies are. There are a few different packages that might be more interesting. There's an important note. The internal transistor inside can either be a bipolar transistor or a MOSFET. If it has a C in the name, the internal transistor is a MOSFET. Else it is a bipolar transistor. This might have some application for a particular project. If you need currents instead of voltages or voltages instead of currents, or if you're working with really high voltages, you probably want a MOSFET instead of a bipolar transistor. They also come in dual packages. So you can have 2 555 timers in a single package, or I think that one has 4 altogether. So if you know that you're going to use 4 timers in a single project, you can just get the whole package altogether. So this is an extra diagram of the monostable configuration I got from my textbook. This is more illustrative. The 2 things that we are missing conceptually are how flip-flops work and how comparators work. After you understand how those things work, you can come back to this diagram and kind of understand what's going on. So challenge. This is the bistable configuration of a 555 timer. What this is really doing is using some clever techniques to use the internal flip-flop as a flip-flop. Oh shucks, I have not used a flip-flop in a hot second. But the idea of the flip-flop is that you have a one input says, am I accepting something or am I not accepting something? And then when that input goes from high to low, it stores whatever value was going into the other one. So here they use K and J. So I believe it's like if J goes from high to low, whatever value K was at that point is stored in the flip-flop. That is explained in much greater detail and much better than I can if you take a course in digital electronics, or if you just look up how flip-flops work and get that a little bit more. But they are very useful in storing values and et cetera, et cetera. I think they're also called multi-vibrators. Are there any questions about Electronics Club or 555 timers? All right. And there's that's a 555 footstool. It's popular enough to get plushies and footstools made out of it. All right, that is the end of our meeting. Our next meeting will be determined around next semester. See you guys then.